What's up, all you badass mathematicians? So, today we're going to continue exploring the applications of calculus by talking about machine learning. So, there are two main aspects of any machine learning algorithm. And so, the first one is the prediction function. So, in machine learning, you're often trying to solve some real world problem and figure out some value, some prediction for some unknown value that you're interested in. So this will be done with our prediction function that we're going to call f hat of x. So it's going to take in some input about the real world that we know and then predict some output that we're interested in, but we don't necessarily know. And so the second aspect is our fitting method. So this fitting method is really the learning part in machine learning. So how are we going to improve our prediction function to give us the best possible predictions it can? So, for instance, if we had a prediction function that was quadratic, ax squared plus bx plus c, then our fitting method is then going to figure out the optimal values of a, b, and c. So let's really try and take a look at this in the context of an example. And let's say we have the following data. So x and y coordinates, 1, 1, 2, 1, and 3, 2. So this is some input that we know, and here are some example outputs. So this is called the training data. So this is how we are going to get our initial guesses for our parameters of our prediction function. So then there's often some test data. X and Y. And let's say 4, 5, and 6. So this test data, we don't actually know the outputs, the y value. So we're trying to create as good a model as possible just using the training data so that we can then apply this to our test data. So let's try and plot our training data. All right, so we have 1, 1, 2, 1, and then 3, 2. So one thing we're trying to figure out is how good is our prediction. So we're going to have some prediction function, and we're trying to get feedback about how good our function is. So for this example, our prediction function is just going to be a line through the origin. So f hat of x is equal to mx. So note for different values of m, so let's say this is m equals 2, and this is m equals 1, maybe this is m equals 1/2. So when we change the value of m, each of these values of m is going to have an associated loss. So for example, so our loss associated with a slope of 2 is going to be equal to. So we need some way at each point to get feedback about our loss. And then once we add over our loss at each point, then we can figure out what our total loss is. Now notice that it's really important that we make sure our loss is positive. And the reason that this is important is because negative loss and positive loss should be penalized the same. So you can imagine if at x equals 1, we have a loss of 10, and at x equals 2, we have a loss at negative 10, then our total loss should be 20. instead of 0. This is why it's important that each element has a positive loss. So if we're looking at a slope equal to 2, then maybe our function, so f hat of 2, so let's go item by item. So f hat of 1 minus y1 is 1, plus f hat of 2 minus y2, which is also 1, plus f hat of 3 minus 2, which is y3. So remember, this is going to be our prediction with each of our input points in our training data set. So we know that our loss always has to be positive. So one issue we might run into here is f hat of 1 minus 1. Well, what if f hat of 1 is 0, for instance? What if we chose m equals 0? Well, then that would make our first term negative. So one way we can guarantee our loss is positive is by putting an absolute value around each term. So this is one possible way. And while this is helpful, we're actually going to use another strategy to make sure all of our losses are positive. Just because it will make it easier to apply our tools from calculus. So instead of taking the absolute value, let's try squared loss instead. So we know if anything squared will always have to be positive. So then this is equal to, so if we're looking at L of 2, that means m is equal to 2. So remember, our loss is actually a function of our slope. So f hat of 1 is equal to 2 times 1. 2 minus 1 squared plus f hat of 2 is equal to 2 times 2, which is 4 minus 1 squared, plus f hat of 3 is equal to 2 times 3, which is 6. 6 minus 2 squared. So this means our loss is equal to 1 plus 9 is 10. 10 plus 16 is 26. So maybe we can improve this value. So maybe we can calculate this for L of 1 and then figure out an associated loss with L of 1. So we can do this quickly. If f hat of x is equal to x, then 1 minus 1 squared plus 2 minus 1 squared plus 3 minus 2 squared, which makes this equal to 0 plus 1 plus 1. So our loss is a lot lower when we chose a slope of 1 versus a slope of 2. So now notice it becomes an issue because we'd have to just guess. Like now let's do L of 1/2, and then, but what if L of 3/4 is better? So how can we figure out which one of these slopes is actually going to be our best choice? So this is where our tools of calculus will come in handy. So we already have our function, our loss function, which we'll call L of m, because remember, it's a function of the slopes. So each one of these losses is associated with a specific slope. So now we can write a general expression for our loss as a function of our slope. So L of m is equal to, so f hat of 1 minus 1 squared plus f hat of 2 minus 1 squared plus f hat of 3 minus 2 squared. So we can also write this in a general expression for those of you interested. So from the summation from I equals 1 to n, which is 3, because we have 3 data points in our training set, of f hat of xi, so our specific input, so x1 would be 1, x2 would be 2, x3 would be 3, minus the actual real output for that value, so what's in our actual training set, squared. So this is a more general expression. So now we can say that this is equal to f hat of 1 is mx minus 1 squared plus, oh, sorry about that. I can actually plug in here. So this is m times 1, because we know our value of x, minus 1 squared, times m times 2, minus 1 squared, plus m times 3, minus 2 squared. So we're trying to figure out the m that minimizes our loss function L. So this means what we're going to do is set L prime of m equal to 0. So L prime of m is going to be equal to 2 times m minus 1 plus 2 times 2m minus 1 plus 2 times 3m. Oops. And what did I forget here? I forgot chain rule. So 2m minus 1 squared, the derivative of that power rule, bring out the 2, times 2m minus 1. Chain rule says we multiply by another 2. And chain rule says we multiply by 3 out here. So 3m minus 2. So this is going to be equal to 2m minus 2 plus 8m minus 4 plus 3 times 2 is 6, so 18m minus 12, which is going to be equal to 2m plus 8m is 10m plus 18m is 28m. 28m minus 2 minus 6 minus 18 is equal to 0. So this tells us that 28m is equal to 18, which means m is equal to 18 over 28 is 9 over 14. And now, are we done? But wait, have we actually even confirmed that this was a max or a min? So all we've done so far is say that slope of 9 over 14 is a critical point. So it's also a good idea if we take the derivative again, maybe do the second derivative test, or confirm using the first derivative test. So the second derivative test tells us that L double prime of m is equal to 28, which means our function L is going to be concave up. So therefore f hat of x equal to 9 over 14 x will minimize loss. And we can say that m equals 9 over 14 is a local min by the second derivative test. So essentially, to recap what we went through is we've introduced the idea of machine learning, which is essentially just a prediction function and a way to optimize that prediction function. So here in our example, we decided on a prediction function that was linear and going through the origin. So our model became just mx. Now, our one choice for our different lines is just by varying different values of m, and each of these choices is going to have an associated loss with it. So to optimize that loss, we're going to take the derivative and set it equal to 0 to determine critical points, and then use the second derivative test to actually confirm that it's actually a minimum. And once we've confirmed that it's actually our minimum, then we have actually found the slope that minimizes our loss. All right, so thank you for listening. Please feel free to leave any questions or feedback in the comments. And thank you. Have a good one.